do today. So our last unit, my goal is to try and cover all of the reactions that we have remaining before I leave by the end of the week, which means that next week with the sub, it may feel a little bit like a tutoring time where you get better than a tutor. You get a PhD organic chemist lecturer to come in and answer questions and work on things with you. You also have all of the practice finals. So if you are not sure about how to prepare for the final, then you should just come in here, put in some headphones, and start a timer, and then time yourself on the final. That way, when questions come up on one of those practice exams, and questions will come up on those practice exams, you've got Natalie here to answer questions for you. She's not going to be recording lectures. I certainly can't ask her to do that. So the only way you can take advantage of her is if you come to class. If you don't come to class, then this week is the last week of your summer semester. I will be sending lecture videos that will help you with doing the exam review, lecture videos that will help you with learning these reactions.
She's doing 3 classes next week and 2 the week of finals?
That's right. And the finals week classes were always going to be review periods anyways.
Sick. Thank you.
But if we are able to get through the last of our reactions this week, she might not have to teach new material next week either. You're welcome. It really will just be come in with the questions that you have. You guys also know that if you don't want to come in for class, there's free tutoring at the STEM Center. I've got a link on our homepage under the course resources that shares the hours for the organic chemistry tutors. Okay. Well, let's start off with everybody's favorite and do some nomenclature. Oh, you know what? Actually, I wanted to review something about our reactions because Elvira came in with this question. When you look at this structure, this is what we call a halonium ring, in this case made of bromine, so a bromonium ring. This is a symmetric halonium ring, meaning both carbons are equally substituted. And although there is a formal positive charge on bromine, bromine is not partially positive. Bromine here is a partial negative, and the 2 carbons are partial positives. So when a nucleophile, something that is negatively charged, comes in to react with this, the nucleophile is not drawn to bromine's formal positive charge. That positive charge tells us bromine wants electrons back. It doesn't want more electrons, it wants its electrons back. So in order to get electrons back to it, a nucleophile is actually drawn to the partial positives. When we have an asymmetric halonium ring, meaning one carbon is more substituted than the other carbon in the ring, what we find is that the bonds to bromine are not symmetric. One carbon has a much shorter bond to bromine, and one carbon has a much longer bond to bromine. You can see that in the way that I've drawn it out. Why do the 2 carbons have different bond lengths? Well, it has to do with stabilizing this partial positive. The carbon that bromine is closer to still has a partial positive because of the electronegativity difference and the size difference of carbon and bromine. But the carbon that bromine is bonded longer to has a much larger partial positive. I wanted to give Gavin some credit for showing this on his mechanism on the unit test this week. You showed this type of partial charge distribution, which helped remind him about where the nucleophile should attack. The idea that one of these bromonium rings has 2 partial positives equally sized, so the nucleophile might be drawn to one or the other. That's great, because it doesn't matter where it attacks. But here, the nucleophile is actually drawn more to the larger partial positive. And that carbon holds a larger partial positive because bromine is further from it. And bromine is further from it, leaving a larger partial positive because a more substituted carbon stabilizes a partial positive better. And now the nucleophile, whatever it is, whether the nucleophile is bromide or water or some alcohol, the nucleophile is always drawn to that more substituted carbon.
But the nucleophile is only going to that carbon on the right because you drew the bond that way. You draw it the other way, right? And have it going to the left.
Okay, tell me if you mean this.
Yeah.
Sure. So it's not about left and right, is it? It's about more substituted and less substituted. That's the regiochemistry term we have to apply here. The secondary carbon can support a positive better than the primary, and so it does by allowing the bromine to stretch further away from it, regardless of whether that more substituted carbon is left or right. Yeah?
Yeah.
So where's the larger partial positive here?
Right there on the more substituted carbon.
Good, on the more substituted carbon. Good. The other thing, Elvira brought up this question from active because she was struggling to see what arrows she needed to add on active in order to take the intermediate that you were given and get to the next intermediate. So my recommendation to her was map your carbons. And there's a lot of correct ways to map your carbons, but mapping means whatever numbers you give them in one intermediate, you give that same numbering in the next intermediate. Now, she chose this numbering, which was to start from the halonium ring and number to the right. Remember that this is not the same as assigning locants in nomenclature. Mapping is all about, can I see the change that's happening at the specific carbons? I would have actually mapped this a little bit different. And I didn't share this with her earlier because I wanted to share it with all of you. The way that I would have mapped this is actually from the nucleophilic attack. That's how I like to map my reactions. But the nucleophilic attack, what's the nucleophile in this reaction? In this step, rather. The oxygen is the nucleophile. The alcohol is the nucleophile. The nucleophilic attack then comes from the oxygen. So I would have actually mapped my oxygen as one of my atoms. Now, I get that's not technically mapping carbons because we're mapping in oxygen, but it's still useful. And I want to figure out where that oxygen attacked. So I'm actually going to look at the bottom and I'm going to map like this. I'm going to map this 5-membered ring. The oxygen has bonded to carbon 2. Nucleophilic attack, forming a new bond. Oxygen attacks carbon, bonded to 3, 4, 5, which takes us back to oxygen. That's how I formed a 5-membered ring. If I am not confident about which of these carbons is carbon number 2, I can just work backwards from 5. Oxygen 1 is connected to 5, 4, 3, 2. So by looking at my product and saying oxygen bonds to carbon, that's going to become 1, 2. And then looking at how they're connected back to each other, I can actually work backwards to figure out where 2 has to be. And now I can make the prediction about the arrow pushing, which follows the partial charge reasoning that we were just talking about. The oxygen is attacking the more substituted carbon because there's a larger partial positive, because it's more substituted. Okay, mapping your carbons, very useful practice. And then reasoning too, remembering the partial charge distribution. All right, let's talk about nomenclature. There weren't any more questions on this, were there? Our rules for nomenclature so far have been identify the parent chain, and that is the longest continuous chain with the highest priority functional group. what I'm going to say functional groups, plural, in parentheses, meaning sometimes there might be more than one highest priority group that you want to get. Sometimes there might only be just one. Once you've identified the parent chain and you give the root, then we identify the suffix. And that's either ein, ein, or ein, if the compound, if the parent chain contains both an alkene and an alkyne, then both can appear in the suffix. But
you say can, but is that a required rule?
Well, yes, we can have instances where actually a part of the molecule, like a substituent, has an alkene or an alkyne, in which case it would have to get named as a substituent. So if it can't be part of the parent chain, if I can't get both the alkene and the alkyne in the parent chain, then they don't go in the suffix. They'd go in the prefix. So what I mean is, also by can, we don't see ein or ein. Only ein get combined. Ein is only used if there is no alkene or alkyne. Yes, yeah, we will. Now, alcohols also show up in the suffix, but they don't provide a suffix. The hydrocarbon provides a suffix. The alcohol gives a stopper. So the alcohol takes ein and creates ein-ol. So we indicate there's an alcohol with the OL. We do the same thing with ene. We drop that E and we get ein-ol. Drop the E on ein and we get ein-ol. Drop the E on ein and we get ein-ol. Old MacDonald had a farm. ein-ol. You cannot just put OL after the root and say that you've used alcohol as the suffix. We don't call it methol. We call it methanol. We don't call it ethol. We call it ethanol. There's still a suffix that comes with the OL stopper. Then we assign a locant set. We want the lowest locant set for the highest priority functional groups. And once again, I'm going to put potentially functional groups in plural, because if you can minimize the locant set for an alcohol two different ways, then you get to prioritize also minimizing some other priority functional group. Let's remind ourselves of what the priorities are. In OChem 1, this is not true of all organic chemistry functional groups. In OChem 1, we're only looking at nomenclature for alcohols, alkenes, alkynes, alkyl, and halo groups. What's the highest priority functional group? The alcohols. So we always want to give alcohol the lowest possible locant. Then wrong. The alkenes and the alkynes, they're tied. So if both an alkene and an alkyne is in a compound, I want to get their lowest locant after I've made sure the alcohol has its lowest locant. But how do I decide between the alkene or the alkyne?
Whatever gets the lowest locant.
Whatever can get the lowest locant. Give the lowest locant possible. What if they're tied? What if one direction gives the alkyne the lowest and the other direction gives the alkene the same lowest locant? A tie goes alphabetically. And what comes first, alkene or alkyne? The ene. So in the case that the alkyne or the alkene could both have the same locant set, the alkene would get the lowest locant because it's a tie going first alphabetically. Then we have our alkyl groups and our halo groups. These are also tied, which is why we have the same rule. Give the lowest locant set possible, regardless of who gets the lowest locant. But if it's a tie, the tie goes first alphabetically. That's it. Those are our rules for nomenclature. So can I have you guys practice on these compounds? I think it's going to work best if you do these in groups. But if you don't want to, we're going to spend the next 8 minutes. I would recommend that you spend your time between writing the name and drawing the structure by its name. So do one problem where you figure out its name, then do a problem where you draw it. Then do a problem where you write its name, then do a problem where you draw it. 8 minutes.
Yeah, the 2-methyl.
But you have to set locant starting at the alkyne.
It could be 3 hexane or hex 3.
I think you're right.
Yeah.
We have to start with not that. Because it gives us a name, so we know that it's That's that one. I was
They're
like,
going to be
well,
tied essentially. So you
um,
do the E because it's alphabetical.
so what are you
So
doing?
1, 2,
So you don't have to start it down.
7.
I think you do.
Oh,
So it would
That just has to
be
be.
2
Does
rows.
it have to
messed
start
up.
there?
You don't have to start there because you can't in this one.
No, you can't.
5 ethyl.
And it doesn't matter, no matter what direction you go.
It's gonna be
3.
1.
So I think it's 2-methyl,
Or you'd say like
1, 2, 3, 4, 5, 6,
No, literally.
one being 6.
1, 7.
So how did you, because if you do it like that, you don't get the longest pair chain, and you have done nothing with these
So
two.
So you wanna start right there. Or no, you wanna start on the other side, sorry.
Hex 1 E 6 and 9. There's a way you can do that.
Yeah, hand the sheets would you do? Would you do 1, 6, and
I don't know 100%.
Close, isn't it? 1-methyl.
But I am probably
2-methyl, structure.
I just do locant, ene, locant, ine.
Mm-hmm.
Like 3 and 2,
I just don't know if you split them up. So you do 1, 6.
Yes.
and
Yep.
or you do 1.
Which is why I put that like that break in there, that hyphen, to remind you you're going to need a locant. Mm-hmm.
separate 1 and 6 to 1 E 6.
The second one, I think it's gonna be
Hi, hi. Yes.
what?
Just that the 2 to 3 bond could be more linear
Like this?
instead of zigzag. Mm-hmm.
That's how it is? Okay.
You've got an sp carbon, which means that everything coming off of it is connected linearly. But I will accept it. I made the same mistakes when I was in OChem 2. I actually went back and reviewed my OChem 2 notes once, and I was like, why are my triple bonds zigzagged? Yeah, it is a challenge, but that was a good fix.
Okay.
You've named them. Make sure you spend some time drawing them.
Yeah.
What do you think of do we incorporate those numerical values? Can we incorporate them at the front?
You can incorporate one locant before the root. You can take one locant in front of hept,
I see. So would it be
but it can only be the first locant, and then the next one still has to be inside the locant, which is why it makes a little bit more sense to just keep both of them in the suffix.
Is correct. 2 bromo 5 ethyl hept 1 ene 6 ein.
Yeah, the only thing I would change is there should be a hept dash 1 dash and an ene dash 6 dash. And this is all actually one word, so there would be no space.
Oh yeah, you're right. So this would be together.
Yeah, not even dashed.
So, can you do it like this, where it's 1 6 heptanine first?
And then a hyphen 2 bromo dash 5. Say what?
Can you do it like that, 1 6 heptanine?
You can, yes, but you have to tell me where the alkene is and where the alkyne is.
Yeah.
Saying 1 6 doesn't actually clarify for me which one is the alkene, which one is the alkyne.
So do you have to put it inside where it's 1 ene 6 ein?
You could have 1 heptene 6 ein
Okay.
or hept 1 ene 6 ein. So only one locant can ever be written out front.
Got it.
So I would say it makes more sense to have both inside.
Because I don't, you never see him draw the 3 lines all the way down.
Yes.
So,
We're torn.
we don't know if there's a carbon here, and that would
Yes.
be an ethyl.
So that is,
So
This is what I.
It's
the
the
alkyne is coming off an ethyl.
or the alkyne's part of the methyl.
it's a 2 carbon
Okay.
alkyne. All alkynes are 2 carbons.
Yeah.
Right.
But I know it's not a bend, but it is an end of a triple bond. So that tells you there is a carbon there. Yeah.
So which one is right?
So if it was a methyl, would the 3 lines go all the way down to the triple point?
If it was a methyl,
It wouldn't be. Yes, they would just be 1, 2, 3 off the point.
But it wouldn't work because it's.
It would be that would be 5 bonds to the carbon. But what we're not sure about is the number, like which
Yeah.
of these 2 is correct.
well, you haven't actually numbered through your alkene. None of you have numbered through your alkene.
Whoopsie.
You took
That's, yeah, that's tricky.
Okay,
Making the alkene part of the parent and making it
2 bromo.
so.
7 hept? No.
Yes, it is. Yep. So, Chloe, we want the longest chain with the highest priority functional group or groups. And in this structure, we can find a carbon chain that contains both the alkene and the alkyne.
Oh,
So we want to use.
going up.
That's right.
And then, okay.
So rather than making the alkyne a substituent, it will be the parent chain. Even if that chain had continued out forever, we would have named that all as a substituent so that the alkyne is in the parent chain.
Okay, got it. What do you have? 2 bromo, hept 1, 5 ethyl, 6 ion?
Okay, now spend some time doing the drawings below. How much more time do you guys want? Yeah, you love nomenclature. We can, yeah. But I do want you guys to practice all types. So make sure that you move down into some of the alcohols and the drawings.
With phenol.
Phenyl,
Phenyl. We forgot what phenyl was.
a benzene ring.
Oh, that's right. Okay, so that includes, but it's a 1 phenol.
So it comes off of carbon 1.
Yeah. So it's like And that's right. You said it's a benzene ring. So it's
Oh, well, you have just turned carbon 1 into one of the carbons in the ring. Off of carbon 1 comes an aromatic ring.
so it would be like this.
Good.
And aromatic rings are pentagonal, right?
No,
They're hexagonal.
hexagon with 3 double bonds, alternating double bonds.
Okay. So your last day that you'll be here with us is Thursday. Is this your last class on Thursday too, and then you just go, or you have labs too?
I have a lab in the afternoon, yep.
Okay.
Oakham 2 lab.
And then you're gone.
Mm-hmm.
Dang. Are you allergic to anything?
No, but I don't need anything.
Are you sure?
Uh-huh.
Do you have any dietary restrictions?
No, no. The only feedback I'd give on this is straightening out the alkyne,
Yep.
which helps me figure out how many carbons you're actually going for. So to me, this looks like 1, 2, 3, 4, 5. That's actually pentyne
Yeah.
rather than butyne, which should just have 2 carbons, or sorry, 4 carbons.
Yeah. So if you get rid of this one,
Yes, I agree.
and straighten that out.
And then if it can get straightened out, it makes it even easier to actually identify how many carbons you're meaning. I would say a good way to start is with the zigzag, draw in the triple bonds, and then re-sketch it, straightened out. Yes?
Well, 2 questions. They build on each other.
Okay.
Is that correct to that?
Yep.
Okay, so then, second part, why is it not 1, 2, 3, 4, 5, 6 hexol hexane?
Because you use like dibromohexane. You know what I mean?
Hexahydroxyhexane.
Oh, okay, we're just making things.
All, OL is a suffix. So it has to go at the end where the suffix goes. Suffixes go at the end historically, famously, notably.
But isn't technically ain also? I guess what I'm just saying.
Yeah. Ain is actually the suffix. All is what I call a suffix stopper. Or I call this stopper suffix up there.
So it's just basically like we know that the suffix
Stoppers.
stopper goes at the end of the end, not the beginning of the end.
Yes. So take this for example, the simplest alcohol.
And then you put the alkyne on the second.
1 carbon, meth. No alkene, no alkyne, ane. Alcohol functional group, all.
So I guess why isn't this hexane? Oh, because there's 6.
Because you have a multiplier, yes. So when we had those multipliers for the diene and triene, we actually saw that an E comes back. We drop that E to make space for the OL. But this compound, CH2, OH2, a diol, geminal diol. This is methane diol. And you can see we've got that di multiplier. And because of that, the E comes back. I will say, I'm not this nitpicky when you have to do naming on an exam. I don't look for all those small little things. I look to see that you've got the right things in the right places. So if you gave this to me without that E, I'd get it. But if you gave it to me without ane of some type, that would cost you some points for not having the suffix, right? So what you're looking at is hexol. Because of that, the E has to come back in for ane. Methane, hexane, hexol. We could call those all substituents. We could call it hexahydroxyhexane. The alcohol as a substituent group is a hydroxy group. But we can include it in the suffix, either hexahydroxyhexane or hexane hexol.
So if we made it a substituent, would it go ahead of the hex?
Yeah, because substituents always go in front.
Okay,
Right? Like 1 phenyl is a substituent to 2 butyne. So the 1 phenyl came in front. 4 phenyl comes in front. I guess I didn't do a lot. These will have some substituents. Are you guys ready?
Yeah.
Do you want to start by giving me compounds that you know how to name? This group here, do you have any on the board that you want to name? Okay, Delaney, first come, first serve.
2-methyl hex 3-ion.
Great. So you recognized that no matter which direction you number, the alkyne is going to be at position 3. Number from the left, the alkyne is at position 3. Number from the right, the alkyne is at position 3. So we've already minimized the locant set for our alkyne. Then we minimize the locant set for whatever else is lowest. Because there's a tie for the alkyne, we get to put the methyl group at 2. Great.
Okay, number 2. We have 2 bromo, 5 ethyl, hep, 1 ene, 6 ine.
Awesome. Now, how did you decide to start from the alkene and number 2 the alkyne?
Because alphabetically it's going to be that way anyway.
Because both of these were terminal, we're going to start at one or the other. We're either going to start numbering from the alkyne and number towards the alkene, or from the alkene, and we said if it's a tie, it wins alphabetically, alkene wins. So our bromine gets to be at position 2, our ethyl at position 5. Great.
And you don't factor bromine into that decision at all, right?
Bromine and the ethyl had no weight in that. None.
I
If-
just did it based off of which one would give bromine the lowest substitute following this order.
That's bad.
Because it should be the alkene and the alkyne that you worry about.
You see how bromo is down here as priority 3, and the alkene and the alkyne are up higher, and it's already determined by the alkene or the alkyne. Either the alkyne is at position 1, and the alkene is at position 5, or the alkene is at position 1, and the alkyne is at position 5. Those are our 2 options, full stop. And we have a rule for it. A tie goes to the first alphabetically. So now everything else just falls in place. It is different than this one, where actually the locant was determined by methyl, because it was the same for the alkyne either way. Here, it's not the same either way. It's either lowest for the alkene or for the alkyne. So we stop after that. Gavin?
I'm sure you mentioned it because you underlined it, but it says pen 3 ion 2,5-diene.
Yes. I didn't mention it yet. I messed up on that one. Ene comes before ine. I don't know why I swapped the ene and ine. So this is what it should look like with ene and ine in their correct positions. You'd be able to get the same name either way.
How do you have,
Or I'm sorry, you'd get the structure either way, but I just named it wrong.
wouldn't having an ene on a 5 make it a hex?
That might be another problem with my yes.
I was gonna say this is like
Impossible.
it's like it's adding 5 bonds to 3 and 4.
So this should be hex.
Yes.
Thank you.
We were stuck on this problem.
Does anyone want to name the compound on the top right? Michael?
4 bromobutes, 3 ene, 1 ine.
Anybody disagree?
1 bromobute, 1 ene, 2 ine.
You said 4 bromobute, 3 ene, and 1 ine. Now you've numbered from the left to the right, so your alkene started at 1, alkyne started at 1, alkene at 3. If you had numbered from the right, your alkene would have been at 1, your alkyne would have been at 3. Your alkene and your alkyne were tied. They're both 1, 3 in either direction, and a tie goes to the first alphabetically. So this one would be better named 1 bromo, bute, 1 ene, 3 ine. Good. Was that another one that you were confused by the bromine? What do you think got you there?
Yeah, I think it was the bromine.
Kind of the opposite direction, where you thought you had to maybe give it the lowest locant possible? Okay. All right, 1 hexyne Listen, I've told you guys that a good way to draw compounds by their names is to start with the parent chain. Hex, 6 carbons. Then put in the alkenes, put in the alcohols, put in any other substituents. And in this case, it wouldn't matter which side gets the alkyne, but it's going to be the far left or the far right. Now, I'm not a big fan of this because it doesn't respect the sp hydrogens, the sp carbons linear geometry. So I would redraw this. Now that I know what it kind of looks like, I would redraw it so that at this carbon, it has a linear geometry. Carbon 5 is sp. I know that's the opposite of the locant set numbering, but this is mapping more so than locant set numbering. I just wanted to number it a certain way. That's not wrong. You guys are okay with that? It's kind of a challenge when you need to do it right for locants, but if you're just mapping, it doesn't matter.
Is mirror image okay?
Mirror image is absolutely fine. I know that this is a challenge though, drawing these out linear. Keep practicing with it. I think it's easier when you draw it by hand because you have that actual break in the line. But I know that on the worksheet, it's hard to identify how many carbons are where when that center line of the alkyne bleeds right through. So keep familiarizing yourself with the idea that if that line bleeds right through, here's the stop of a triple bond. There must be a carbon there if the triple bond ends at that point. Okay, 1-phenyl 2-butyne. Here's a 4-carbon chain, bute, with an alkyne at position 2. And then off of position 1 is an aromatic ring. I'll draw out the aromatic ring in a minute, but we can also abbreviate the aromatic ring as just pH. That's what phenyl is meaning. Not a fan of it because when I come in to look at how many carbons you actually have, if you haven't drawn it very cleanly, for instance, if you drew something like this, I'm going to look at that and count extra carbons because I already told you that I see this as an end and a bend. So take this 4-carbon chain and then straighten it out with the alkyne and then put the aromatic ring in. If you want to draw the aromatic ring completely, that's great. If you want to draw it as pH, that's great. Okay, my problem here was naming this pent and then trying to have you give me 2,5-diene.
How does it even
I was
work
gonna
with
say, it
that?
doesn't make sense because it still gives,
You still have a 5 bond.
Yeah.
the other side of the triple bond.
Shall we just toss it? I've screwed that one up, I think, enough that it's not even worth considering. Sorry. So you all realize that you can't do it. Awesome. Good.
Maybe that was the lesson.
More nomenclature down here. Who wants to name these?
I'll try.
Okay.
Except that it's probably wrong because I gave it to Broman.
Which one do you want to?
I just said.
Did you follow this? Give the lowest locant set for the alcohol. Give the lowest locant set for the methyl and the bromine last. Did you start at the bromine?
Yeah.
Okay.
Well, actually, no, I started counting at 1, but I named it 4-bromo, 1-methyl, cyclohexanol.
Okay, so you didn't start at the bromine.
Yeah.
Where did you start at?
The alcohol.
Yeah, exactly. In a ring, it doesn't matter where you start. So start at the highest priority functional group. In that case, you did it exactly right. 4-bromo, 1-methyl. Remember that these are alphabetized. Cyclohexanol. And I don't have to say what carbon the alcohol is on. Why wouldn't it be? I get to start wherever I want in a ring. I don't get to start wherever I want in a chain. I get to start wherever I want in a ring. I'm going to start at the alcohol. So I don't have to say that. Is it wrong to say 1-all?
No, it's not. It's more precise.
It's more precise.
Not needed.
It's not wrong. It's not necessary. But if you said something like 1 methyl, or let's say you said 1 bromo, 4 methyl, 4 cyclohexanol. That is wrong because you didn't prioritize the alcohol correctly. All right, second one. Anybody? You've done enough of them. I think you can take a break. You're welcome.
Take a shot at it.
Andrew.
5-dichloropentane-2-ol.
I hear dichloro, but I only heard one number. If there's 2 of them, I need 2 numbers.
So it'd be 5,5-dichloropentane-2-ol.
Good. 5,5-dichloro pentan-2-ol, or pentane-2-ol, or 2-pentanol. Perfect. That is another common mistake. I get why it happens. Both of my chlorines are on position 5. So I can just say 5-dichloro, but actually I want to verify that they're both on 5. So I'm going to say 5,5-dichloro. Michael and then Delaney.
Is it correct to add, like, you could say 2-hydroxypentanol?
Only if there was another alcohol there. For you to say 2-hydroxypentane-2-ol, first of all, you didn't give the locant for where the alcohol is. If you're going to say hydroxy and ol, that means you're actually describing 2 different things. You're describing one alcohol as a substituent. You're describing one alcohol in the suffix. So you could call this 5,5-dichloro 2-hydroxypentane. Or 5,5-dichloro 2-pentanol. The alcohol is distinguished either as a prefix, a substituent, or in the suffix as part of the parent. Good question. Okay, last one.
I will give it a shot.
Okay. Oh, actually, I didn't answer Delaney's question.
That's okay.
Thank you, Patrick.
Why is it pentan? Can it just be pent?
Pent-2-ol? No, that would be like taking methanol and naming it methyl, which we don't do. Because OL is not OL is not a suffix. And that's what I messed up here. This I meant to call a suffix stopper. OL requires a suffix to already be there. So it needs the an of ane, right? Because there is no alkene, there is no alkyne.
Right.
Patrick?
Would be 4-methyl cyclopent 3,4-ene-1,2-ol diol.
Sorry, 4-methyl cyclopent 3.
3,4-ene.
Oh, we only list multiple numbers if there are multiple alkenes.
Oh, sorry, 3. Just 3.
3-ene.
3-ene, 1,2-diol.
Good. And actually, because we're going to have di, the E comes all the way back. Whew, that's a long one, huh? Well done. This one really clarifies the priorities rule. We know we're going to start with one of the 2 alcohols. And we know we're going to number toward the other alcohol because both of those alcohols need their lowest possible locant set. So either we start from the alcohol on the left and we number right, or we start from the alcohol on the right and we number left. Both options give us 1,2-diol. Great. So now my alcohol has gotten its lowest locant set no matter where we go. Then we move down the list. How do I get the next priority group, its lowest locant set? Well, the next priority group is the alkene, and I'll get there sooner by numbering from the right to the left counterclockwise, which means that the alkyl group's placement wasn't a priority for us. That just happened to be where it was. In fact, 4-methyl, we could have gotten there, we could have gotten a lower locant for methyl, but not with prioritizing alcohol and alkenes. Okay, with these last two, I really like this 1, 2, 3, 4, 5, 6 hexane hexol. This is a chemical known as, I screwed up. No, I forgot. Sorbitol. Sorbitol means like the sugar tree or something. So they named this something about a tree that gives sugar. It is a sugar. It's a sugar. There's many sugars. This is a sugar. All right, and the last one, once again, we've got that but3-ine. So I'm going to start with my alkyne. I'm going to draw this straight line off of it and then a bend. And I know there's going to be a bend because it's not a 2-butyne. It's a but3-ine. So out of the 4 carbons, the alkyne will be on the last. Now, we're saying the alcohol shows up at position 2 and the alkyne at position 3. Off of position 4 is a phenyl. And that means that the phenyl is actually connected to the alkyne.
Wouldn't that be a 5-carbon
Parent.
bond?
If we draw out the aromatic ring at the end of that chain, we will remind ourselves that we can't count a carbon as part of the parent, or we can't count carbons that are both inside a ring and outside a ring. We can only count within a chain or within a ring. So 1, 2, 3, 4 carbons in this chain,
It's not directly attached to it.
and then the carbon of the ring. Yep, the 4th carbon in the chain, and then the 1st carbon in the ring. But those can't be counted as part of the same parent. This compound could have also been referred to as 3-hydroxy 1-butynyl benzene. If we wanted to make benzene the parent chain, then that linear stuff coming off becomes a substituent of benzene with a hydroxy group on the 3rd position and an alkyne group on the 1st position. So it'd be a 3-hydroxy 1-butynyl benzene. I think this actually looks nicer. How do you feel about nomenclature? Okay, that's all I'm going to ask you to be able to do with it. I mean, we've talked about R and S configurations getting put into nomenclature as well. Not that challenging. Whatever chiral carbon has a configuration, just goes in the front. We've talked about having E and Z character in our names. There weren't actually any E or Z things for us to consider. Now, I want to introduce alkynes a little bit, and we're going to be going through their reactions. In terms of the regiochemistry of an alkyne, yeah, I should have probably introduced alkenes this way too. Alkene regiochemistry, we said that they could be non-substituted, mono-substituted, di, tri, or tetra-substituted alkenes. Alkynes have much fewer degrees of substitution possible. We have acetylene, which is the smallest possible alkyne. This is a non-substituted alkyne. And don't get me started on the fact that the name acetylene has "ene" in it. I wasn't around when they decided that name. That's a terrible name, isn't it? Acetylene, what alkene do you see? I see no alkene. Also, a misnomer for sure. Then we have terminal alkynes. Terminal alkynes have one bond to carbon, but one bond to hydrogen. The alkyne sits at the end of the chain. I want you to think of this being similar to a terminal di-substituted alkene. Because it ends the carbon chain. And then we have internal alkynes. An internal alkyne has a bond to carbon on both sides. Which type of alkyne can undergo both Markovnikov addition and anti-Markovnikov addition? Okay, so we've got the gambit. We've got somebody saying each of them. What is Markovnikov's rule?
More substituted, the hydrogen will have more substituted carbon.
Markovnikov said hydrogen adds to the carbon with more hydrogen. Which carbon here has more hydrogen? Equal amounts in acetylene. They both have a hydrogen. Which carbon here has more hydrogen? Equal. The internal alkyne has 0 hydrogens. So acetylene and internal alkynes do not have regio distinctions. They don't have regio-selective environments. Equally substituted, equally substituted. The terminal alkyne has regio-selective ability. The terminal alkyne has a more substituted and a less substituted carbon. That's really what I want you to take away from this.
What's going on with that terminal alkene that you did there?
Mm-hmm.
Why is that there?
Just as a reminder that we had used that term before to describe the difference between an internal di-substituted and a terminal di-substituted. Remember, the internal di-substituted was either cis or trans.
Right, versus the terminal.
Yep.
So then with an addition reaction, Markovnikov or anti-Markovnikov would apply to terminal alkenes.
Markovnikov and anti-Markovnikov only applies to terminal alkenes. Alkynes, excuse me.
Or alkenes, yeah.
Although that's true, it also can apply to terminal alkenes like this, but more significantly, in this context. You guys are okay if I erase all the nomenclature stuff, right? You got that all? Don't need a picture of it? Okay. If we want to form an alkyne, then we do so by elimination, because to form pi bonds requires elimination. But unlike with forming alkenes, forming an alkyne requires a double elimination. So it requires 2 halides leave and 2 beta hydrogens leave. Where are the 2 halides here?
The bromine on that methyl group.
Good. We describe these as a geminal dihalide. Why? Any Geminis in the class? We talked about this. Gemini, and I don't bring up star signs because that's something you need to know for this class, but I bring up star signs
It was an OK Ruby.
because it is related to how they named this stuff. Gemini star sign is the twin star sign, and these halides are twins. They're on the same carbon. So it's a geminal dihalide. So obviously both of those halogens can be used to form an alkyne, but I also need to remove 2 hydrogens Where can I remove 2 hydrogens to make an alkyne? At the end of the methyl. The tertiary carbon to the left of the dihalide doesn't have 2 hydrogens to lose. So the alkyne that can form here, terminal alkyne. By the way, if you tried showing the other version, drawing an alkyne to the left, you might not be surprised that one of my OChem 2 students submitted a mechanism for their unit test where they gave me several intermediates that were 5-bonded carbons. It is a simple thing to forget about, but I want it to make you feel uncomfortable when you look at that.
Yeah, it does.
It looks weird. It should look weird. It's wrong. Okay. Keep going with the others. How many alkynes can you form? Oh, you know what? Sorry. I wanted to give you the other types. The one that you see beneath it, or sorry, to the right, is not geminal. Do you guys know what term we use for this? Aquarian. No. These halides are not twins. They're not on the same carbon, but they are neighbors. They're on adjacent carbons. We call them vicinal. This is a vicinal dihalide. The other way that we can make an alkyne is if we're already halfway there. If we're able to take a vinylic halide and remove the halide and again a beta hydrogen. Those are the 3 ways that we can make an alkyne. And actually, we're going to see on the back side how the vinylic halide is an intermediate of these dihalides. First, one halide is removed and 1 pi bond is made. Then another halide is removed, another pi bond is made.
Like 4-step mechanisms.
2 steps. Go ahead and predict the other alkynes possible for those remaining structures. And I know I skipped over one of them, so I'll draw that one up. Just like with the alkenes, we're just trying to show what alkynes can be formed. Great work, Delaney. Why don't you walk her through how you predicted that?
I did it in pen and I wasn't paying attention, so I just started rewriting.
That's
it.
good. That's great. That's a great way to do it. Actually, just start with what you had and then figure out where the alkyne will be. Good.
Okay, but we know like
Good, Kayla.
bonds break, right? So let's tell us what's after this story.
You know, there's nothing wrong with this, but having your groups come into the vertex I would never recommend it.
Oh, okay.
I would always say your groups should come out of a vertex, like how mine, you see the bond line goes up, and then the group comes out of it. Yeah, bond line goes up, group comes out of it.
Oh yeah, I did
Your
the
bond,
opposite.
your bond line comes up, and then your group comes down into it. I wouldn't recommend it because it doesn't follow geometry.
No.
If you wanted to assign chirality, like let's say you made this a wedge or a dash, and you wanted to assign chirality, you can't. You won't get it right. And it's because it actually doesn't reflect how the molecule physically arranges itself in space. And that's all chirality is, right? Chirality is just how it arranges itself in space. So when we draw that misrepresented, we can't represent its absolute configuration. 9 times out of 10, it won't bite you in the butt. But that one time that it does, it's a big bite.
Can you explain why do the 3 hydrogens here mean that this can form it?
Well,
How does A?
I have 3 hydrogens. 2 of them need to be removed along with my 2 halides if I'm going to be able to make 2 degrees of unsaturation. Think about mapping your carbons. If this is 1, 2, 3, 1, to, there's a third carbon. So this halide gets removed and that hydrogen makes a double bond. This halide gets removed and that hydrogen makes another double bond. 2 double bonds.
That makes sense.
Triple bond. Okay. We'll go through the mechanism, and maybe that will help it make more sense.
But that does make
Good.
I'm sorry, I wasn't paying attention while you were lecturing.
Mm-hmm.
So
We are,
we're just like removing the halogens.
we're trying to figure out what alkynes can be made.
If we remove.
We did the same thing with alkenes,
Okay.
and we said the leaving group needs to leave along with a hydrogen adjacent to it.
Okay.
But now I don't want to make 1 pi bond, I want to make 2. So both halides need to leave, plus a hydrogen adjacent to both of them.
Okay, so I can hear like what the bromines leave and they all just kind of mush together.
Both the bromines leave and 2 of the hydrogens from the methyl group leave.
And they're all just like kind of fold in.
Yep. So one Br, one H leaves, double bond forms. The other Br, the other H leaves, another double bond forms. Yes. Help. Need somebody. Not just anybody.
So,
Yeah.
I don't know why this one's linear and these aren't, but
Yeah.
so the what I'm confused about is it always going to be like between halogens or what's the whole leaving group situation?
Yeah. So these elimination reactions are neither oxidative nor reductive because we remove electrons with a leaving group, like the bromine, who owns those electrons. But then we also abstract a hydrogen who leaves electrons with the carbon.
That are free to go.
So one carbon loses its electrons to bromine, the other carbon shares its electrons from hydrogen.
So is it always going to be around? How do you know which one is the leaving group?
We call the halides the leaving groups.
Okay, so it will be around the halide.
Yep. The carbon with the halide will be one of the carbons
Yeah.
in the alkyne and in the alkene.
Okay. That makes it easier. It's not just going to
Yes, because, so,
It's between like.
Mm-hmm. There is another one here that can form, but these are great.
Okay, so there's 2 configurations.
That's right.
That's what I was wondering.
2
So, 'cause it could
structural
go-
isomers.
It could go this way or it could go this way.
That's right.
Okay, that makes sense. Do you want me to draw both?
Yeah.
Do these look okay?
Great. Yeah.
Which of these carbon bonds would it go to?
Show them both.
It'd be either one.
That's right.
Because they're equally substituted.
That's right. Yep. So if it can do both, it probably will do both.
Which ones? We just drew them zig.
oh, right, that actually.
Zigzag.
What is that?
It's like not even zig zig. It's just like zig.
Yes.
What is NC? Is it exactly what I think it is?
It's actually CN. What do you think it is?
Carbon, hydrogen?
Sure, with enough bonds to satisfy their octets. So it's a carbon-nitrogen triple bond. It's cyanide if it's CN minus. It's cyano if it's a substituent on a group. Or it's nitrile. You guys ever worked with nitrile gloves? The gloves are made of a polymer that probably have cyano groups on them. Is it nitrile instead of nitrile?
I have no idea.
Anyways, tomato, tomato, acetyl, 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 acetyl.
Miso meso.
Touche.
Why do you say miso? Sorry.
All right, so for the vicinal dihalide, we should see a triple bond form between those carbons 3 and 4. So we form an alkyne between the 2 vicinal carbons of the dihalide. The vinylic halide forms an alkyne. And then here, where I have a geminal dihalide and 2 hydrogens on either side, I'm going to map my carbons here so that I can see how an alkyne might form between carbons 2 and 3. An alkyne might form between carbons 3 and 4. So one of my products is between 2 and 3, and then 4, 5, 6. And my other product is between 3 and 4. Notice how I'm using the mapping to try and make sure that my atoms are connected correctly, that I have the right carbon chain, that I've got the bonds in the appropriate space. It's so easy to mix up the structure.
Is this also a geminal?
This is a geminal dihalide. Great. Okay, so you can see how alkynes can go through elimination. Look just beneath that, and let's decide what these alkynes could have been made from. Either, no, actually, give me a dihalide starting material for these compounds. No, you don't need to give me a reagent. Give me something like this. You don't have to tell me how it becomes that. By the way, this big arrow, this is like a what? A wide arrow. This arrow means retrosynthesis. In other words, we're saying, what did this come from? It is really strange to have an arrow pointing forward at something, but that's like saying that's the past. You might equate it to, like in politics, if you've got a law that passed and then it points at a historical event that led to the formation of that act.
Would we know which halides were used in the reaction?
That's your guess right now.
What could
What could make it?
Ones that pair together, like bromine or chloride.
Yeah, so you're going to need a dihalide.
Yeah.
Don't do the vanillic halide for right now. Start with a dihalide. So either geminal or vicinal. What carbons do you want them to be on? And you might think about, will this give multiple products, or will it give that alkyne exclusively? Feel free to draw as many as you can think of. How many different alkynes, dihalides could make these? I think that's too many halides.
I was too lazy to draw it twice. So
I see. Then very smart then. You've got it. Great. Great. Any other versions?
Yeah.
Great.
There we go.
Great.
Working on it.
I think you missed a methyl on, yeah. Are you in the same boat as?
Yeah.
It's okay. She's got 5 bonded carbon, so that's good. That was great. Both of those separately would form just that alkyne exclusively.
Does it matter if I did different colors?
No.
If I put this on a test, would I get it wrong?
Yeah. Yeah.
What if I specify?
If you're doing it on a test, I would just say take the time to draw them out separately. Hello. Great. Yes.
I haven't gone there yet.
That's okay. Awesome. Yep. Those are the possibilities. How about this one? Can you do the one on the right? How could you make 1-butine? Mm-hmm. Yep. That's one version. And I can think of 2 others.
2 others.
What do you mean, like?
for the.
Yeah, that's good. That's one version. And there are at least 2 others that you could do, but that...
Because there's hydrogen available on either side.
Mhm.
So it would be like, you could put one here or here. Right?
Yep.
So...
Well, not here.
You're
That
right,
would be in the
'cause
wrong
that's-
spot.
Because there's a... Yeah.
But here, that would give the position. In fact, the structure that you've drawn could lead to different alkynes besides just that one. If you want to see how they're made, you can look in the back where it actually, we're going to go through the synthesis. Yeah.
With this one that you were just showing me, why could it form on this one when there's only one hydrogen available?
Well,
Don't you need two?
there's two hydrogens available there.
Yeah.
And the alkyne is going to form between the carbon with the halogens and the carbons adjacent to it.
I see. So
If we call the carbon with halogens alpha, then it's a beta hydrogen that gets removed. And you were looking past beta.
yeah. So because like it's 1, 2, 3, 4, 5.
Good.
1, 2, 3, 4, 5. Between so you're saying between.
We
3,
want
4,
it to
and
be between
5.
3 and 4.
Okay, I see. So between, and I put mine on 3. So
Your
you're right,
halides are on
okay.
3.
It could go either way though.
Your
Halides
hydrogen-
bonds to 4.
Yes. You could make 3 to 4, you could make 2 to 3, just like this one. So the structure you have can form the one we're looking for. It could also form a structural isomer.
So it doesn't matter that carbon atom 5 only has one hydrogen available.
Never going to be involved in the elimination. Yes. Yes, but I don't want you guys to worry too much about predicting vanillic halides.
Professor, is there another way we can do this? Quinn did it kind of.
Yeah, so is that right?
Can that be?
Yep.
Okay,
So you
cool.
went with a geminal
Okay.
dihalide.
So it can just be.
She's gone with vicinal. Absolutely.
Okay. That work?
Very cool.
You've gone with a vanillic halide, and that would work. I just didn't want you to have to worry about vanillic halides yet.
Okay, but it would work because you're only having to create one bond.
Yep.
With the hydrogen.
Exactly. This is missing a methyl. That's all.
Oh yeah. But then this one, it would be like breaking that one, that one.
Yes. Yes. Perfect.
Does this one work as well?
That would actually form 2-butyne. The one on top works,
Yeah.
but the one in the middle, you've got a halide on 2 and a halide on 3, a vicinal dihalide. So your triple bond is going to form between 2 and 3, not between 1 and 2. That can work, and there's at least 2 others that also work.
Like this, something like that?
Yes.
Okay.
Yes. And there's one more. All right, shall we go through them? They don't have to be on the same carbon. Good.
Right, okay, so does that mean for that second one, it could be off one, carbon 1 and 2? Is that what you were saying?
Yep.
Okay, that makes sense.
So let's leverage this idea of mapping our carbons. If I map my carbons 1 through 6, I see that my alkyne here is between carbons 3 and 4. So I need 2 halides, either both on 3, both on 4, or 1 on 3, 1 on 4. If I put both my halides on carbon 4, the alkyne that forms might form between 4 and 5, or between 3 and 4, which means a dihalide with both of the halides on carbon 4 has different products that it might make. Not necessarily the best option for what I want. Not great. If I put both of them on 3, we actually see what we saw before, where only one direction can form the alkyne and the other direction cannot. But if I split them 1 on 3, 1 on 4, then it's a no-brainer. The alkyne only has one position that it can form. So those 2 on the bottom are best. The one on top works, but it gives some other products as well. 1-butyne looks like this. Once again, if I'm mapping my carbons, I either want a geminal dihalide on carbon 1, a geminal dihalide on carbon 2, or a vicinal dihalide between carbons 1 and 2. If I form, or if I use a geminal dihalide on position 2, I run the same risk of actually getting 2-butyne as a product. So it can work, it just might not be the best option. But if I run a geminal dihalide on position 1 or a vicinal dihalide between positions 1 and 2, those work perfect. This is to say, there are a lot of different ways to run a reaction to get the same product. Structural isomerism can be leveraged to actually maximize how many different products can be used, can be made, or minimize how many products can be made. Saray.
Make sure we're using the right reactant in our experiments.
I think this question gets a lot more into the nuance of being an organic chemist. For instance, it might surprise you how easily accessible some compounds are, but how hard it is to access their structural isomers. So it might be that 1,2-dichlorobutane, super easy structure to purchase, super easy chemical to purchase, inexpensive. And it might be that 1,1-dichlorobutane is expensive and hard to use and hard to work with. So I would say knowing which one is best goes beyond the scope of our class. Knowing that there can be multiple routes, that's the scope of our class. And then if you ever get into the context where you have to choose between a route, you will have to just, that's where you'll approach a new frontier of learning. How do you decide what chemical is best?
Kind of like, how would you leverage which formation? Like,
sometimes you cannot.
it's just random.
Exactly. And we know how to separate getting different things. We can run column chromatography, and we can actually separate out these different molecules from each other by chromatography. So if we ran a reaction, let's say this one, and we wanted to get this, but we know we might also get a structural isomer, we get them both. We separate them out by chromatography, and then we just use the one that we get.
Could you rerun the isomer multiple times until you possibly get the alkene or alkyne?
Usually if this reacted to form a mixture of both this and the other alkyne, no, it'd be really hard to undo it and try it again. Essentially, it just becomes waste. That happens all the time. You make multiple products because multiple products are possible, and then you separate them, take the one you want, and toss the rest of them. Sometimes unavoidable. Although a lot of chemists, they do their work on trying to avoid waste, maximizing efficiency in a reaction. All right. The synthesis of alkynes is an elimination reaction. Oops. Synthesis of alkynes, elimination, as opposed to addition to alkynes. And we're going to look at the addition reactions. This requires a very strong base. We will leverage, sodium hydride when you see that Na bonded with something, I want you to think Na plus. What does that make H? H minus. Hydride with a negative charge. So when you see this, I really want you to just think H minus. H minus as a base is very aggressive because its conjugate acid is H2. H2 has a pKa around 44. Which means H minus is a very strong base. We also work with NaNH2 sodium amide, which is an unfortunate name because it's not an amide carbonyl. It's an amide ion. IDE telling us, again, negatively charged. When you see this, I want you to think NH2 minus. I don't even want you to draw a covalent bond between Na and H or Na and NH2. because there is no covalent bond. It's an ionic compound. And when this acts as a base, it forms ammonia. Ammonia has a pKa around 35, which means that this is also a very strong base. So we've got this elimination. What I'm going to do is actually demonstrate the arrow pushing for you. I believe at this point that you can predict the arrow pushing for this. You have all the tools necessary. What bonds form, what bonds break. And what directions should electrons flow. So when we look at this, we see that one CH bond breaks, one CX bond breaks, and one carbon-carbon double bond forms. When the carbon-halide bond breaks, the electrons go to the halide. So halide is going to leave, which is why we call it a leaving group. It takes electrons and leaves the molecule. The CH bond breaks, and the CH bond is owned by carbon. So carbon can donate the CH electrons to its neighboring carbon and form that double bond. Who's going to take the hydrogen? Our very strong base is going to act as a base and make carbon the acid. Now I know that that's strange because we said earlier in the semester carbon is not a very good acid. In fact, carbon has a pKa, and sp3 carbon has a pKa in the 50s. So why is the pKa low enough for it to do this? Well, it's got inductive effects from these electronegative atoms nearby. The electronegative atoms pull electron density towards themselves, making the carbon more acidic. That gives us NH3 as a byproduct. Now if we take a second equivalence, what do we need to show on that second intermediate? Same thing. So amide acts as a base, steals a hydrogen. The CH electrons form a double bond. No, a triple bond, because there's already a double bond there. And the halide leaves, and we're left with our triple bond. How does this change when you look at the bottom direction, where instead of a geminal dihalide, I've given you a vicinal dihalide? The only change is, what intermediate are you going to draw? And which halide and hydrogen do you need to steal in order to make that happen? Let's say that I ran this one with sodium hydride, and we know that it does the same thing. It forms the same intermediate. Which halide should leave to form this intermediate? Which beta hydrogen should be stolen? Good. Notice that the halogen on carbon 3 in the middle stays to form the intermediate that we have. This halogen needs to stay. So the carbon on the right, that halogen needs to leave, which means that it's the beta hydrogen on top that is stolen. Two groups have to leave from two different carbons in order to form a pi bond. One of the most common mistakes I see here is students taking the same hydrogen and taking the hydrogen and halogen from the same carbon. I'll see students that deprotonate and kick off a halogen from the same carbon. But you cannot form a double bond if two carbons are not both losing something. Both carbons have to lose in order to form a double bond. Which is why we call these reactions beta hydrogen elimination. Beta hydrogen implies what? Beta hydrogen implies an alpha carbon. Gavin?
Did we deprotonate it twice? Is that why you have NH2 2 in there?
Yeah, and I didn't really show it out here. We'd actually have two equivalences of ammonia formed.
But would you also have like an X2?
Yes. Yeah, I didn't show that, did I? Ammonia and X minus, because it's replacing the amide. Which means out here it would be X minus and X minus. It actually wouldn't be X2, which would be an oxidized version of those. Good call.
On an exam, would you be looking for those as well, the X minus?
No.
On the outside?
No, not as often. Those are the byproducts, and showing the change to the substrate is more important. Okay, Gavin,
Silly question.
tell me.
Is the, what we're seeing here, the H minus, is that a base? And then the NH2, is that minus, is that a base? Is there accepting hydrogen?
Yes, they are. NH2 minus is a very strong base.
So they're forming conjugate acid with H2 and NH3?
Ammonia is their conjugate acid. Molecular hydrogen is the conjugate acid. And in terms of being an acid, very bad acids. So that makes them good at making this equilibrium work.
Very strong bases from the acids.
Would the molecular hydrogen turn into a gas or would it stay in the
It's going to bubble out. The ammonia might as well. The ammonia will bubble out.
This phase is hydrogenation, right? That's why we're using the bubbler.
Yep, this week you're going to make hydrogen gas and bubble it into a reaction. Okay, thank you guys for your time. We're going to go through more reactions tomorrow and Thursday, and we're going to just keep applying it. Listen, you have all of the tools on this worksheet that you need to be able to solve the roadmap on the back. What we are going to go through is radical stability. We're going to talk about radicals, but you have all of the reagents that you need to be able to start applying these new reactions. We're going to cover them, but don't hesitate to move forward.
We're gonna